Chapter 12.1, Part 4, The Age of the Universe. By the end of this section, you should be able to define Doppler effect and explain its application to the light from other stars and galaxies. Stars emit light. So, we are observing the light emitted from stars and galaxies. And this is the way we get the information of stars and galaxies. So certain stars are millions and billions of light years away, and there are billions of galaxies. So only thing we get from these stars to get information from them is light. So using just the light that comes to us from these stars or galaxies, we can get a lot of information about those stars and galaxies. So we will see how we can use the Doppler effect for this. Use the equation for redshift. The amount of redshift Z is given by these equations. Delta lambda divided by lambda. So this is the change in wavelength. That is the difference between the observed wavelength and the original wavelength, divided by the original wavelength. Original wavelength is the wavelength of the waves that the source emits. Okay, then similarly, delta F divided by F. So this is the difference between the observed frequency and the original frequency, and this is the original frequency. In other words, original frequency means the frequency of the wave that the source emits, but the observed frequency will be different from the original or frequency of the source, because either the source is moving towards the observer or moving away from the observer. So we will learn the details about this later when we learn about the Doppler effect. Then it is also equal to, amount of redshift is also equal to V divided by C, where V is the speed of the source of waves. Okay, so for example, if it's a star and if it's moving at a certain velocity V, that will be the V. And C is the speed of light. The speed of light, now since we are dealing with stars, the stars are traveling in a vacuum. It's in space, it's in a vacuum. So that is the speed of light in vacuum, which is approximately equal to 3 into 10 to the power of 8 meters per second. Describe Hubble's law and the equation V equals h naught d for objects at cosmological distances. Okay, we will again see the details of this. Now there is also a graph for this. V equals h naught d. It's given here. So V equals h naught d, and you can see the equation is given here. V equals, this is h naught, the Hubble constant, times d. If you plot a graph of velocity versus distance, the gradient of that graph will be the Hubble constant. So if you divide both sides of this equation by distance, you will get velocity divided by distance is equal to the Hubble constant. In other words, it is the gradient of the graph of velocity versus distance. So the gradient of this graph will give you the Hubble's constant. Okay, and also what you can see from this graph is, the greater the distance, the greater the velocity. Recession means it's moving away, it's receding. So the greater the distance of the stars and galaxies from us, the faster that they are moving. Okay, the universe is currently expanding. The stars and the galaxies are moving away from us. We are in a galaxy called the Milky Way galaxy. So there are billions of other galaxies, and these galaxies are moving away from each other, and they are also moving away from us because the universe is expanding. And what this graph shows is that the further they are, the greater the distance they are from us, the greater the velocity of recession. And the graph of velocity of recession versus distance will be the h naught, the Hubble's constant, and this equation is what we call Hubble's law. Okay, so this again you can see it over here in the beginning of the chapter. Describes Hubble's law and the equation, this one, for objects at cosmological distances. Now I told you before that this equation can also describe the Hubble's law. Anyway, we'll go through that bit over here. And in this book, okay, so you can see Hubble's law is this. The equation is basically the Hubble's law. And at the bottom of this chapter, at the end of this chapter, the key definitions of the words are given here. Hubble's law is that the recession velocity, that means the velocity that with which a body is, or galaxy, or maybe even a star is moving away from us, the recession velocity of a galaxy is directly proportional to the distance to it. And that is what is shown in this graph. It's a straight line passing through the origin, meaning it's a direct proportion. So if one quantity is directly proportional to the other quantity, in this case the velocity and the distance are directly proportional to each other, then the graph of them should be a straight line passing through the origin. So for direct proportion there are two conditions, not only in this case, in any case the graph of them should be a straight line passing through the origin, and you can see that over here. Okay, so now you understand a bit about Hubble's law and the Hubble's equation. Okay, so let's start with the Doppler effect. When astronomers first began to look at spectra of stars in other galaxies during the 1920s, they noticed that the spectra looked very similar to the spectra from stars in our own galaxy, but that all the features present were shifted by the same relative amount towards the red end of the spectra. Okay, previously I mentioned about the spectrum of white light, and you learned the acronym ROYGBIV, ROYGBIV. Red has the longest wavelength, violet has the shortest wavelength. So it's ROYGBIV, red, orange, yellow, green, blue, indigo, violet. Blue is closer to violet, so blue has a shorter wavelength than red. So you can see red has a longer wavelength. So if things are moving away from us, for example, you can see this car here is moving away from this observer here. It's moving towards this observer here. So this emits sound with a constant frequency. But even though it is emitting sound or light or something with a constant frequency, waves with a constant frequency, the observed frequency will be different, because the car is moving. If the car is stationary, both this observer and this observer will observe frequencies which are the same frequencies as the source. But if the car is moving, or if an object is moving either towards or away from an observer, the observed frequencies or the observed wavelengths will be different. Okay, so they will feel a different pitch. They will have a different sensation of the pitch. Now you can see over here the car is moving towards the observer. So the car is moving towards the observer means the waves are getting squashed. Okay, so this is emitting waves, the observer is here, so the waves between the car and the observer are getting squashed. That means the frequency is increasing. These circles are the wave fronts. Previously, even in the O-level classes, you all have learned what a wave front is. Okay, so the distance between adjacent wave fronts is a wavelength. So from this wave front to this wave front, that is one wavelength. Now the wavelength here is greater than the wavelength here. So here what is happening is the wavelength is decreasing, the frequency is increasing. So you can see the number of waves in a certain time is more here than on this side. So this observer here will observe a greater frequency than the frequency of the waves emitted by the source. On the other hand, on this side, this observer will observe a frequency which is lower than the frequency of the waves that this car emits. Okay, so here it will be a shorter wavelength that is observed. Here it will be a long wavelength that is observed compared to the wavelength of the waves that this car emits. Okay, so this is basically what Doppler effect is. Okay, so for the definition, again we can scroll down to the bottom of this chapter where all the definitions are given. The Doppler effect occurs when an observer receives waves emitted from a moving body, observes that the wavelength of the waves has been altered to a new wavelength as a consequence of the relative motion. Okay, we will also learn the details about redshift. Redshift is the shift in wavelength of a star spectrum caused by increasing separation between the star and the earth. So what is happening in the case of the star? The star is moving away from us for there to be a redshift. See again, increasing separation between the star and the earth. So if the star is moving away from the earth, or in other words, if it's moving away from us, it is towards the red end of the spectrum. You learned the acronym ROYGBIV, which are the colors of the rainbow, the spectrum of white light. So on the long wavelength side, you have the red. On the short wavelength side, you have the blue, indigo, and violet. So if it's a red shift, that means it has a longer wavelength. That means it's moving away from us. The wavelength is increasing. So like something like this. So you see the car is moving away from this person. Similarly, you can imagine this is a star, this is the earth. So if the star is moving away from the earth, you can see like this, the wavelengths are increasing. So it's called redshift. Red has a longer wavelength. On the other hand, on this side, you can imagine this star is moving towards this. Let's say if it's the earth here, then it will be a blue shift. Okay, but what we have is usually the red shift. Okay, so let's see. The astronomers first began to look at the spectra of stars from other galaxies during the 1920s. They noticed that the spectra looked very similar to the spectra from stars in our own galaxy, but that all the features present were shifted by the same relative amount towards the red end of the spectrum. This phenomena became known as the redshift. This shift is due to the relative motion of other galaxies with respect to ours in an effect called the Doppler effect. An observer receiving waves emitted from a body moving from a moving body observes that wavelength of waves has been altered to a new wavelength. Again, in the definition of Doppler effect also, we saw at the end of this subchapter, the definitions were given, and it is something like this. Now you can see this is when the car is stationary. The waves that it emits will have the same frequency and the same wavelength. The frequency of the waves it emits is not changing. It's emitting at a constant frequency. It's emitting at a constant frequency. So they have the same wavelength when the waves are emitted. But what happens is the observed frequency is what is changing. The emitted frequency remains the same. So if the car is stationary, the emitted frequency and the observed frequency will be the same. But if the car is moving, the emitted frequency is still the same, but the observed frequency will be different. Ahead of the car, the wavefronts are compressed since the car is traveling in the same direction as the waves. In this case, behind the car, the waves are stretched out since the car is traveling in the opposite direction to the waves. The Doppler effect causes a change in frequency and wavelength if there is relative motion between the wave source and the observer. So again, the Doppler effect causes a change in frequency and wavelength if there is relative motion between the wave source and the observer. So what we mean by relative is one has to move relative to the other. Now for example, if there was a car here and this person is also moving towards the right with the same speed as the car, then again it will be similar to this situation because both are moving together. So there is no relative motion. So there has to be relative. One has to be moving relative to the other. If they are both moving at, let's say, 5 meters per second to the right, then it's as if the car and the person are stationary. So then there is no relative motion. So the observed frequency and the emitted frequency will be the same. Okay, so now let's apply this for stars. A receding means moving away. A receding star or galaxy emits light that appear to have a longer wavelength than expected. We also experience this effect, for example, when we hear a car coming towards us and driving past at a steady rate. As it approaches, the note of its engine rises to a maximum pitch. So the pitch increases when it's moving towards you. And then falls as the car travels away, which is this situation here when it's moving away. You could imagine the waves getting squashed closer together, shorter wavelength as the car drives towards you, and then stretched further apart or longer wavelength as it drives away. So here this is what we get in the laboratory spectrum for the stars. Spectrum from a distant galaxy. You know, galaxies are made up of stars. Previously I told you have to know the meanings of these words: galaxy, star. Okay, so we have spectral lines are shifted towards the red end of the spectrum. So in the beginning they were here, but then now they are here. So they are moving towards the red end, which means it's the stars, or in this case the galaxy, is moving away from us. Comparison of light from distant galaxies with light produced in stationary Earth. So this is in the case of the experiment done in the Earth, but this in the same spectrum, same kind of spectrum from the star. So in the case of the star, it is shifting towards this side. So we'll see. Comparison of light from different galaxies with light produced in stationary Earth-based experiments can allow calculation of the galaxy speed away from Earth. Now how do we find the speed? Using this equation, which you saw in the beginning of this chapter. This one. So we can find what is the change in wavelength. Now this is the uh, the original frequency. Okay, this will give. So if the star was stationary, this is what you get, but since the star is moving, there will be a change in the wavelength. So that will, from that you can find delta lambda and lambda. Now Z is the amount of redshift. The amount of redshift a galaxy exhibits, Z allows us to calculate how fast it is moving. Now if this is equal to this, and if this is equal to this, then, and also if this is equal to this, then any of these will be equal to the other. For example, if A equals B and B equals C, A equals C. Similarly, if this is equal to this, and also if this is equal to this, that means this will be equal to this. So we can say delta lambda divided by lambda equals V over C. So delta lambda and lambda, we can find it out from experiments like this. Then C also we know. C is the speed of light. And this way we can find V, the speed of the galaxy. So using delta lambda divided by lambda equals V over C, we know delta lambda, we know lambda, we know C, we can find V. See, this can be done using measurements of either wavelength or frequency changes. Figure B. Let's go through this example. In a laboratory sample, the hydrogen alpha spectral absorption line is at a wavelength of 656.285 nanometers. In the spectrum from a nearby star, this line is observed at a wavelength of 656.315. Now you can see this wavelength here in nanometers is greater than this wavelength here, again in nanometers. So this is what you get in the lab, the first one. In a lab sample, the hydrogen alpha spectral absorption line is at a wavelength of this much. Now the same thing from a star is having a longer wavelength. Why? Because it's moving away from us. In the spectrum from a nearby star, the line is observed at a wavelength of this much. So you see this number here is greater than this number here. How fast is the star moving and in which direction? Now if it's moving away from us, then the wavelength observed should be greater than the original wavelength, and you can see that here. This is the observed wavelength, 656.315. It is greater than 656.285, the original wavelength, which means the star is moving away from us. The wavelength from the star is longer than it should be, so the star is moving away. You can imagine that the waves are stretched. So if the waves are stretched like this, that means it's moving away from us. The wavelength, observed wavelength is longer. Okay, so we can use delta lambda divided by lambda equals V over C, because we are given the wavelengths. If we were given the frequencies, then we can use delta F over F equals V over C. So we are setting this equal to this. We can find the change in wavelength with the difference between these two, 656.315 minus 656.285. So we get 0.030 nanometers. Then we make V the subject of the equation, and we can find what V is, which is what we are supposed to find. How fast is the star moving and in which direction? So the star is the source of light. So the speed of the source is V. Now C is the speed of light in vacuum, which is 3 into 10 to the power of 8. And remember, this lambda is the original wavelength. So don't use the wrong one here. This is the observed wavelength. Okay. This here, what we get in the lab, is the original wavelength. The wavelength from the star is the observed wavelength. So be careful, because sometimes students confuse these two. So here we use the original wavelength, 656.285. Now in some textbooks they give this as lambda O. They write a subscript O here for original, lambda small o there. Then we get 13,700 meters per second. If you convert it to kilometers per second, divide by 1000, you get 13.7 kilometers per second. This is the speed of the star. In 1 second it travels 13.7 kilometers. It's possible because it is occurring in a vacuum. Okay, so that is the example using the Doppler effect. Okay, then let's go to the next part. This image is a composite taken with Hubble's WFC3 and ACS on 5th October and 29th November 2011. It shows dwarf galaxy MACS 0647JD, which is the most distant object yet observed. It has a redshift of about Z equals 11. So what is that Z? This. That is delta lambda divided by lambda, that is equal to 11. Z is the amount of redshift. Z equals 11. Okay, let's learn about Hubble's law. Astronomers quickly realized that redshift implied that galaxies surrounding us were traveling away from us. So you see, redshift means it's moving away from us. In 1929, the American astronomer Edwin Hubble published his finding that the value of a galaxy's redshift is proportional to its distance from us. So that is what you see in this graph. That is, the further away a galaxy is, the faster it is moving. So if the distance is here, you go up and then you can see the speed is greater. So the greater the distance of the galaxy from us, the faster the galaxy is moving away from us. The faster it is moving. Hubble's paper had the same effect on the 20th century view of the universe as Galileo's work on the solar system had some 300 years earlier. Instead of being static, the universe was expanding. The philosophical implications continue to tax the mind of scientists and religious scholars. Section 12.1.5. Okay, so here is the diagram. As virtually all galaxies show redshift in their spectra, Hubble concluded that all galaxies must be moving apart from each other and the universe is expanding. Okay, considering the speeds of objects at cosmological distances, there is a simple relationship between them. This is known as Hubble's law. So very important. V is equal to h naught times d. So the gradient of this graph will be the Hubble constant because it's a graph of velocity of recession versus distance. And the gradient is then Hubble constant, h naught. So the recession velocity, so this is actually the recession velocity or velocity of recession, is directly proportional to the distance to it, the constant of proportionality. The Hubble constant, so V is proportional to D, and if you convert that proportionality into an equation, you get a constant of proportionality which is h naught. Can be found from the gradient of the graph in figure D. This is figure D. So this is very important. The graph is very important. You have to understand it, and you have to understand Hubble's law, Hubble's constant, and Hubble's equation. So here is Hubble's equation. It's also called Hubble's law, and h naught is the Hubble constant. This has had many values over the years, which demonstrates the immense difficulties involved in accurately determining astronomical distances. Since the launch of the ESA Planck surveyor, the uncertainty in measurements and hence the uncertainty in Hubble's constant has reduced significantly, and it is hoped that data from the Gaia survey will improve even more. The value is considered accurate to within 1%, and h naught is equal to 70.9 kilometers per second. Okay, then we have this also. I think you would have not learned this. Okay, in the previous chapter I think we have learned this. Mega per second, per second. So this is to the power -1. It means per second, because this you have already learned the unit of distance, parsec. It's somewhere here. Yeah, see, parsec is a measure of distance. So for more details you can go through this one. Parsec is also called parallax second. Parsecond or parsec, parallax second all mean the same thing. Yeah, so this is the value of the Hubble constant. It's a constant. That's why we say it's a constant. It's a constant of proportionality. It won't change. And the value of that is 70.9 kilometers per second. Although the most recent data give a slightly lower value. See figure A in section 12.1.5. With an accurate value of h naught, astronomers can now also use Hubble's law to determine distances to newly observed objects such as that in figure C. Yeah, so you see like this. something like that. Okay, let's go through an example to help you understand this better. A supernova appears in the night sky and astronomers find that it has a redshift of Z equals 0.45. How far away is the supernova? So now we can use this to find the speed, and then using the Hubble's law equation we can find the distance. So first let's use this equation, Z equals V over C. Now remember, Z was equal to delta lambda over lambda. Also it was equal to delta F over F. Also it was equal to V over C. So we are using Z equals V over C here because we want to find the distance, because we have V here. So once we know the V here, this is a constant, we can find D. So we have V equals Z times C. Z is given 0.45. C is 3 into 10 to the power of 8. Then you will get 1.35 into 10 to the power of 8 meters per second, or in kilometers per second. This is the value. Then according to Hubble's law, V equals H naught D. Then D is equal to V over H naught, which is 1.35 into 10 to the power 5 divided by the Hubble constant, which we learnt, this one. This in here it is kilometers per second, this is the unit, so 70.9. and then remember you have to have the units consistent so that they cancel out and they give you this unit. So it will be 1900 megaparsec or parallax seconds. Note that the speed was found in kilometers per second, as we have the Hubble constant in kilometers per second, mega per megaparsec. Okay. Then about how old the universe is also we can find using this equation. Yeah, let's go through this last bit, then it's complete. As all distant objects show a red shift, they are all moving away from us. This implies that the universe as a whole is expanding. If we imagine time running backwards from the present, then the known universe would contract back to a point where everything is in the same place. This would be the time of the Big Bang, when everything first exploded outwards from that single point. Thus, if we can find Hubble constant, it will tell us how quickly the universe is expanding. From this we can work out when it all started. So let's do that now. The age of the universe can be figured out using this. For an object to travel a distance d0 from the beginning of time at speed v0, the time taken t0 can be calculated from the basic equation for speed. Speed is distance over time. Then we can make t the subject of the equation. If we consider the gradient of the Hubble graph, h0 equals v0 over d0. So we can write the Hubble constant from the graph, you see, v0 over d0. Then v0 over d0 is 1 over t0. Here it's d0 over v0. So v0 over d0 is 1 over t0. So that's what we have here. 1 over t0 equals h0. Then we get t0 equals 1 over h0. So we can find then t0. Note that in this calculation you should use the same units for the distance and for the length components of the units of recession velocity. Recession velocity is the velocity with which it is the galaxy or star is moving away from us. Usually, though the Hubble constant is quoted in units of kilometers per second per megaparsec, h0, you can convert these units to this. Okay, this is in kilometers per second, this unit. Then here meters per second, again the per megaparsec. Then 1 parsec, you learned earlier that parsec or parsecond or parallax second is a unit of distance, and 1 parallax second is approximately equal to this much, 3.09 into 10 to the power of 16 meters. So 1 megaparsec, mega is 10 to the power of 6. So multiply this by 10 to the power of 6, that will give you 1 megaparsec, which is 16 plus 6 is 22. Yeah, so you also have that. Then h0 is equal to so we have this 70,900 meters per second per megaparsec. So 70,900 divided by this one, because it's 70,900 meters per second, whole thing divided by 1 megaparsec. 1 megaparsec is this much. So that's why we are dividing this, which is in meters per second, by this, which we converted to SI units, meters. Then we will get this, and you can cancel out these units and you will get per second. So we know the H naught in SI units, which is this value in SI units. So the Hubble constant is equal to this in SI units. Then we have T naught equals 1 over H naught. Now we learned how we got this equation. That was using this speed is distance over time. Okay, now then we made the time the subject of the equation, and also we had the Hubble constant is equal to V naught over D naught, and then we get this. Okay, so this is the Hubble constant. Now we can find this one, T naught, that will be the age of the universe. This value for T naught gives the age of the universe as 13.8 billion years. You convert this seconds to years, that will give you 13.8 billion years. So that is the age of the universe from the time the stars and galaxies were at one point, were all together. Okay, and then that resulted in a Big Bang where the galaxies started moving away from each other. Okay, then the definitions are very important. Redshift is the shift in wavelength of a star spectrum caused by increasing separation between the star and the Earth. The Doppler effect occurs when an observer receives waves emitted from a moving body, observes that the wavelength of the waves has been altered to a new wavelength as a consequence of the relative motion. Hubble's law is that the recession velocity of a galaxy is directly proportional to the distance to it. So we have V equals H naught D, or we can say V is proportional to D, and the H naught is the constant of proportionality when you convert that proportionality into an equation. Hubble constant is the constant of proportionality in Hubble's law. The Big Bang is the theory that the universe expands outwards from a single point to the currently observed situation. Alright, so that's the end of that, which was about the Doppler effect and the age of the universe. We also learnt about the redshift and Hubble's law.